Everybody, welcome back to yet another Codeforces training. Today I want to talk about binary search, ternary search, and also binary search or the answer, which are pretty beginner-friendly techniques. We'll solve a couple of problems, 5 if not mistaken, and let's see how it goes. So first of all, we'll need our demonstration screen. And let me introduce you to the problem itself. So the most basic version of binary search supposes the following. So we have some array which is sorted, has, let's say, n elements, right? From A0 to AN, and it's sorted. Right, so in increasing order. Potentially non-decreasing, that's it. Some pairs of adjacent elements can be equal, but it doesn't really matter. So sometimes you want to find if an element is present in a sorted array or if it's not, right? So you get some query. You want to find if it's somewhere in the array or if it's not. Now, binary search is a technique to find, to answer this query in logarithmic time. That's it, big O of log n, right? So what it does, it basically says, well, if this element is in our array, and it's either in the left half or in the right half, right? It's left half, and here we have right half, right? So our element is either there, or it's not present in the array at all. How we can quickly check in which half does it belong? Well, we can compare with middle element, right? If our query element is greater than middle, then we definitely know that it's not here. We can get rid of a half an array in just one query, right? Just one question to the array. If our element is, however, smaller, that's it. Yeah, let me write. If a query I is greater than AN, then we want to search in the right, right? If it is, however, smaller, we want to search on the left. And if it's equal to A, we can either include it to one of the branches. Like, for example, here I said that left includes AM. So we potentially may want like this condition to be not strict. Or we can alternatively, if we hit the query, that's it, if we find the correct number in the array, then we can just return, like let's say like found, right? We can usually we return something like true in this case. And after we, for example, we got rid of this half, right? And we divide this remaining part in half, and we get rid of one of the halves, and so on it goes until we are only left with one element, and we can simply check if it's correct or if it's not. Right? So idea is pretty simple. Once you decrease the number of possibilities, the number of places in the array where your query element can go, at each question to the array, you decrease the number of possibilities 2 times, right? You reduce twice, then twice again, etc. And you obviously get logarithmic complexity simply because of the definition of the logarithm, right? So the size of your array decreases in geometric progression. That's it. Quite quickly gets to 1, and then you can just answer. Now, usually you're not faced with problems that sound exactly like this, but sometimes you are. So let me close it so that we can see a couple of problems. For example, like back in 2012, 2013, first problem in Codeforces training that we cover today required exactly that. We were given an array in increasing order, and we were given some queries to it, and we needed to answer like if number is present or not. Well, the way to do it in sort of modern C++ is that once you read your input and stuff like that, you can call std lower bound, right? It takes 2 iterators that are supposed to be random access iterators, and also a value that you want to query for. It will find the iterator to the first element that's at least the value that you queried for. And because it does not want to explicitly distinguish cases when the element was not found and when the element was found, it will return your iterator, and it's your job to check like whether iterator is valid, and if so, you can dereference it and check whether the value is correct. std lower bound, as far as I know, you can pass iterators to it that are not random access, but it won't work in a logarithmic complexity. People often ask, like, for data structure like std set, which clearly should support this operation, right? When you have binary search tree, you can do basically the same. The difference is that you don't your middle is your root value. You don't have to go anywhere to take the middle. You don't have to like, divide the size of the array in half, then query that element in the array. You simply query the root, and it tells you which branch you go to. And because of that, I believe like if you pass iterators to begin and to the end of the set to std lower bound, then you'll get a linear complexity, but there is a method lower bound in std set. So you have something like std set int, I don't know, we have like present butterflies because this problem was concerned with butterflies. Then we can like add some values to it, right? And then we can query like that. It will also return an iterator. So lower bound is the method of class std set. Pretty convenient because it was much easier to like define a class method, I believe, at the time. I mean, you can specify implementation of this template algorithm explicitly for std set iterators, but it's kind of std set iterators by themselves don't provide much information. So that's the way to implement a binary search in std set and not to have nodes of the tree carry extraneous information. Right? So you store only what's necessary in the tree, and at the same time you have a method that can find an element or tell the smallest element that's at least the value you queried for. So yeah, sometimes it's also convenient if you need to like process all elements in sets that are bigger than something, and you don't want to like explicitly loop over the set. Like for example, you can query for one value, then you can query for another value, and you may be interested in processing the all the elements of the set that are at least something and at most something. And you may be sure because of some problem-specific constraints that these intervals are on average small. So that's much more efficient than looping over the entire set and checking a condition for every element. In this case, you will take two iterators. So you'll take first iterator, and you'll take another iterator for upper bound for a different value, and you will loop from one iterator to another using iterator increments. I believe you can increment std set iterator because that's the purpose of an iterator. Yeah, so that's pretty much this for first problem. But again, usually you are not faced with a problem like that. Usually you have something more interesting. For example, you don't have an array explicitly, but what you have instead, that one reason why array may be not given explicitly is because it's very long. For example, you have values from 0 to 10 to the 9th, and you want to find smallest values that satisfy some condition, right? Obviously, you can't explicitly generate the array, but you can do the same thing. So you maintain your left value, you maintain your right value, you query for the middle, and you ask some question of middle. We can denote this question as f. Let's say if it returns true, let's say that f of right is initially true, and f of left is initially false. And what you want to find is the first value when f of m is equal to true. For example, you know from the problem that it's initially false and then it's true. You're interested in this job. You can do the same thing. Like if you query for f of m and you get true, it means that a function is true all the way here. And because of the structure, somebody told you that small values don't work, large values work, and you're interested in finding minimum values that will work. So if middle works, then all of this works, and you are not interested in it because you're searching for the minimum that will work. If minimum, however, doesn't work, like if you have false here, and you're not interested in this part, because at the beginning you have all falses, then you have all true. So if middle does not work and zero doesn't work, then everything in between also does not work. So you're again left with the same kind of intuition to dissect the range of possible values into two. And if you're looking for the smallest values that will work, or that huge values will work, small values won't work, you're looking for the minimum elements that will work. You can't generate the array explicitly because it's too huge, so you just maintain three numbers, left, right, middle, and query middle and update right and left as you should. Right? If f of m equals false, then left can get middle. If f of m equals true, then right can get middle. This way, your interval decreases 2 times, which again leaves you with logarithmic complexity. And don't be scared of this value being huge. Again, a log of 1 billion is approximately 30. Right, because a log of 1000 is 10, and this is the cube of this, so log gets multiplied 3 times. So logarithms are pretty small. You don't have to be concerned with them usually. Let me remove unnecessary part. Well, sometimes you may have like not necessarily a question in which gives like an answer of true or false, but a function f that is increasing, and you want to find, like, you want value of f to be at least, like, I don't know, some constant. You want to find smallest value of x that will work, right? It's the same thing. You can just convert this function f greater than equals to c. Like this is a graph of f, right? A graph of f greater than equal to c. Like this is a Boolean expression. It returns 0 or 1. So you get 0 here before this x and 1 here. So you can easily convert like real valued functions to what's called binary predicates, or I should say unary. I'm not sure how to say the word. Let me check. So effectively what I'm trying to say is that you have a predicate that's something returning Boolean value, and it takes in one argument. Unary, right. Unary predicator. So it takes one variable, therefore it's unary, and it outputs binary value, therefore it's predicate and not function. Like function outputs real values, predicates output Boolean variables. And this example of like how do you convert real valued function to unary predicate is often encountered in what's called binary search over the answer. For example, you're given you want to satisfy some conditions, like you know that and you can select one variable. You have like one variable in pretty complicated problem, and you want to satisfy some condition. That's the same if you know that like small values don't satisfy the condition and large values satisfy the condition, then you again remain with unary predicate. Let me show an example of such problem. So we have a classical problem really calls into stalls. So we have several stalls on the real line, several points in which we want to place our cows. And we want to maximize the minimum distance between cows. So between adjacent cows, there are several pairs of adjacent cows, and we want to maximize the distance between them. How do we do it? Well, we can first define binary search. I personally like to define it as a template because this way you can pass also things like precision, which will be useful when you, like, so far we were only working with integer values of the argument to the function, right? Further on, we'll work with real values. So our function can be real, it can take in a real argument and still output Boolean value, and we can perfectly deal with that. The only difference is that, well, we won't be able to find the answer exactly, but we'll be able to calculate with it with arbitrarily small precision. So here's nothing interesting, just my template. You generate middle value, you avoid overflow, because sometimes when you add lower bounds and upper bounds, you can end up with overflow. This way you never end up with overflow, I believe. Then you check a condition at middle and change lower bounds or upper bounds accordingly. And I believe that the function is written in such a way that I return the last argument that gives a value of false, or no, the last that gives value of true, right? So in this version, I have like, initially we have true, then we have all false, and we're looking for the last value that returns true. It doesn't really matter, you always can convert one to another by taking the negation. Like your Boolean function will return something just before it returns, change the condition so that it returns the opposite set. And such a template, as you can see, we make use of std function. You could possibly just don't write the type explicitly and define another template parameter, but I like it more this way. It allows us, in the main program, we'll think only about whether a given argument, whether middle satisfies some condition or it's not. So here we check whether or not we can achieve distance between calls. Yeah, by the way, it should be a distance between calls. So we check whether or not we can achieve some given distance. How do we check it? We do, in this problem, we do a linear scan. So initially, we are located at the very left of the real line, then we encounter stalls. If current stall is valid, so we can put echo into it, and the distance to previous stall with echo will be large enough. Then we put echo and update the current last stall. Yeah, so just a couple of statements. We maintain how many cars we put in. We maintain what's the previous occupied stall. Whenever we are able to add another call, we do it, and we also update the previous occupied stall coordinate. And then, again, we wanted to place our cars. We were given some number of cars. We wanted to place them all, so we can just check whether we placed enough cars. So this way we convert like a real valid function of how many cars we are able to place with given distance to whether or not we are able to place enough cars. Yeah, so just like that. Also, it's pretty convenient that you can define lambda functions that can also capture context. Because, for example, here I need stall coordinates, but I don't want to pass them to the function explicitly, so I just capture this variable. And I also do this by reference, not to use too much memory for copy, right? Just like this, you can do binary search over the answer. Now, the next problem is a bit more interesting, but let me first go to problem D. Problem D is concerned with finding a root of cubic equation. And we are also guaranteed that there's only one root, which is not really necessary for the algorithm that we are going to use, but it guarantees uniqueness of all our answer in some way. So we are given coefficients of a cubic polynomial. We want to find its root. We know that it indeed cubic, that its main coefficient is non-zero. We also want to find it as a real number or with at least 6 significant digits. What is the possible way? Well, we know that every cubic has at least one real root because, well, let me take like x cubed minus 17x squared. I'm not sure how it looks, but if you substitute x gets minus 1000, then let's say even like plus 17x squared, right? If you substitute something really large in absolute value but negative, then this thing will be very, very negative. That's it, 10 to the 9th. And no matter what goes there, you will get negative value. That's it. And on the other hand, like when you make plus 1000 here, and no matter how negative these coefficients are, this will be positive. It will be 10 to the 9th, and it will be like minus 17 million. Then we don't really care about everything that's not main coefficient when we substitute large values. So that's it. We have some real line, right? Here is x, here is f of x, our cube. Now that when x is very small, the values are negative. When x is very large, the values are positive. That's it if main coefficient is greater than 0. So if you have like 3 here, and it's so. Case when it has minus is really symmetrical. For example, when you change all the signs, the root does not change. So we won't be really concerned with it. This condition effectively says that, well, we need to go from here to there, and no matter how we do it, we will always intersect line f equals 0 at least once. And if we are guaranteed that we intersect it only once, then we again remain with our classical problem. So here the value is negative. Here the values are positive. And we are asked to find this point. Well, again, we do binary search. We know like from the bonds on from the constraints on our coefficients, we know that roots are from minus 10k to 10k. Doesn't really matter how big of a constraint you get there. I guess like 10 to the 9th will be still like very fast, so you don't have to be precise. I think it's correct. I think actually correct is around 1000 plus 10 or something like that, but I didn't want to find the exact value and decided to be rather conservative with my bounds. I mean, like if I multiply bounds by 2, by a factor of 2, it will only take me like 2 more iterations. I don't really care. I can afford it. And you can as well, right? So just give some reasonable bounds that won't fail, okay? Here you again take the sign of the cubic to get like either negative or positive. And you can see it here. We defined our cubic explicitly. And then we just ask whether it's positive or not. And because I am a bit lazy, I also used like binary XOR to check that exactly one of this condition holds. That's it. If a is greater than 0, then I actually want to check that this value is negative, and when a is smaller than 0, then I want it to be positive. You can write if-else statements in lambda function. That's totally okay. But I decided to go with this version. And notice how our template hasn't really changed. Even though we're now using long doubles, we can just change the template's parameter. I guess it sometimes can infer itself, but not always. Like for, yeah, not always. I'm not sure if it always can infer. And also we give like precision. It would be enough to give like 10 to the power of minus 7, I suppose. Minus 6 is a bit risky. Minus 7 is totally okay. But we can also get like 10 to the minus 10s, right? Again, it's like we multiply constraints by 30 times, but this 30 gets quickly removed. Very quickly removed by division by 2. So like, we multiplied constraints 30 times, but it only took us like 5 or 6 more iterations to go. So again, you can be very conservative with constraints if you are not doing many binary searches. In this case, I'm doing only one, and I'm given an entire second. I don't know. I can find it with precision of 10 to the minus 1000, if of course floating point arithmetic supported that precision, right? So yeah, that wasn't really interesting problem, but you know a very nice mathematical fact that every polynomial of odd degree always has a real root. In particular, every cubic polynomial has a real root. And we have another problem that is a binary search over the answer, and binary search has not changed indeed. But this time we want, like, we need a little bit more. Our unary predicate got a bit longer because it's a bit more difficult to check whether the given value works or not. Let me quickly cover that problem and we'll get back to problem C, which is about ternary search as promised. So in this problem, we have trains. We have a schedule according to which, like, first train moves for first v1 minutes with no, for first t1 minutes with velocity v1, then for t2 more minutes with velocity v2, etc. So we're given some segments on which train moves with constant speed, and we want to multiple trains to depart with some interval. The distance between them will obviously change because they move with, they are currently on different intervals in their schedules. And because of that, they have different velocities. So the distance between them will change. And we're interested in the minimal possible interval that we can depart trains with that interval, so that distance between them never gets less than some safety regulations recommended distance. How to do it? Well, I compute like times at which something happens. So we have timestamps of events. Event is like speed changes, right? The reason why I want it is because trains, the distance between trains is linear on every segment. So when no trains change their speed, they just move, possibly at different speeds. Distance between them changes linearly. And because of that, like, linear function always takes minimum value on either one of the ends, endpoints, right? So I can just check if the distance is long enough in the endpoint. That's it's when one of the trains change its speed. So I know that first train changes at T1, T1 plus T2, T1 plus T2 plus T3. That's why I compute prefix sums. I also know that second train changes its speed on like the same times, but plus a train departure interval, right? Then I just like partial sums are already sorted. These are also sorted. And now, in fact, I'm left with two sorted arrays of events that I want to merge. And I just do it explicitly by iterating over them. You don't have to, you could generate the second array. So just take this partial prefix sums, add train departure interval to every element, and then you can merge two arrays. There is std merge in linear time, it works. But you can also merge explicitly if you want to. I didn't want to use extra memory, so I decided that I'm going to merge explicitly. And it's just as simple as it is, like when speed doesn't change, that you know how much time passes until the speed will change of any of the trains. And during this time interval, next time minus current time, each position changes by corresponding velocity times this time. So nothing really interesting. You just simulate how a pair of train moves on the line. You know that you want to look against the minimum distance between them only when some event happens. So some train changes its speed. Just like that, we check after this is simulate one step. You want to calculate when the time when next the first train will change its speed, the time when second train will change its speed. You want to update positions. You want to update indices. And at the very end, you want to check like whether the distance between trains is valid or not. If it's too short, you can immediately signal from that function returns value. Otherwise, you keep going. If you processed all events, then you are good. Your trains don't collide, I guess. And yeah, so this function returns whether or not a given train departure interval is valid, so whether or not it results in too short distance between consecutive trains or it doesn't. And because we have this function, we now can just apply binary search. So really, all the logic of the program was in this unary predicate. Binary search hasn't changed at all. Some helper read array hasn't changed. Returns vector. If it's given some size, then it reads the array of the corresponding size. If you don't give a size, size is 0 by default. I suppose that you don't give like a readme array of size 0 on purpose. So we can use 0 as special value. And if it's 0, then we can read it from the input as well. It's really convenient because with this you can for example, like the only reason why I read this variable explicitly is because I need it later on. Otherwise, I could just do this, and it will read the size of the array first, and then a corresponding number of elements, which is something that you quite often see in competitive programming, is that you first given the size of the array and then the array itself. So with this construction, you can read it with one statement. Potentially, you can use shorter variable names if you're into this. I'm not in a hurry in these training sessions. I try to write reusable code. For example, here, this was not necessary. Yeah, so this binary search, it has not changed, but now we can use it with a different type. And also we can pass specific precisions that we wanted to work with. It's really convenient template. I guess it sometimes can derive type as such, or potentially even as such. But in this case, it failed, I guess, because here I was taken, I don't know, maybe I needed const reference to long double or something, but obviously don't have to. So yeah, I guess like writing type template argument is not all that long. You can spend a couple of minutes, a couple of seconds on writing this name instead of rewriting your entire binary search for a different type. Okay, I guess this is it for trains. Like this code, if you want to check it, it's available on GitHub in the same directory as you will see the statements. And let's head on to the last problem, which is kind of interesting. Let me actually, yeah. Sometimes you don't have a monotone function. So we had like function like this. Obviously, you can also have function like this when you take minus f. If this is f, then you can take minus f and you will be left with function like this. So these two are not really different, but sometimes we have functions like so or like so, and they are called, I believe, how these are called actually? Unimodal, I guess. They have only one mod, so to say. In these cases, you are sometimes interested in finding maximum value or minimum value. Again, if this is f, then you can convert by taking minus f to the same shape as this. So we'll only cover this shape. So we have a function that looks something like this. Yeah, let me. And you want to find its peak value on a segment from left to right. Now, one possible, like if you only query for one middle element and you don't really know what's going on, because what you see is effectively a picture like this. Here's your middle, here's your right, here's your left. You have no idea whether the function is like this or like this. And so you can't decide which interval to go to. What you can do instead, you can query for two middle values. So middle that's sort of lefter and middle that's sort of righter. I guess there is no such word, but whatever. And then you will see one of the following situations. So left or middle, right? Okay, yeah, at least it's hilarious. You will see something that is, well, potentially you will see like strictly increasing for values. And you definitely know that maximum is somewhere here because you can't have like peak here and then another peak here because it's not unimodal. In this case, you know that you have to look on this interval, and it's actually very convenient because you like if these segments are of the equal length, that you in binary search you decrease, like you get rid of the half. Here you get rid of 2/3. So you're kind of more efficient. However, you may end up with a picture that looks differently with something like this. Then you, well, at least you can get rid of this interval. Because MR is clearly, like there is clearly some peak from ML to R. Then you can get situation like this. So it increases, decreases, decreases, then you can get rid of this. And if it constantly decreases, then you can again get rid of both these two intervals. So in any case, you get rid of at least one sort. And people sometimes think like, well, if I get rid of one half, then I'm obviously converging somewhere, but what if I'm getting rid of one sort? Well, it's the same thing, and you can see it very clearly if you take two steps. So first, we have like one distance from left to right. And we get rid of one sort. What are we left with? Well, we have two sorts left. So for example, we got rid of this part. Then we say like, okay, then we get rid of one sort, but not from one, but from two sorts. From the current value, we multiply it by one sort and we subtract it. And as you can see, like this value is 2/9. This is actually, if you multiply by 3 both numerator and denominator, you'll get with 6/9. So you remain with 4/9, which is effectively less than 1/2. So every 2 iterations of ternary search, you remove as least as many elements than in one iteration of binary search. So in the worst case, ternary search will converge in 2 times the number of iterations needed by binary search. 2 times log n is still asymptotically log n. Now, a couple of problems where you can encounter unimodal constraints. Some physical problems. For example, here in Firewood Meadow, we want to travel from point 0, 1 to point 1, 0. Let me draw it. We have like, I guess we are here. We want to get here, but like here is a forest and here is some field. And we obviously travel faster on the field than in the forest because now you have to avoid trees, etc. So probably we would like to travel more on the field and less in the forest. Sort of light reflection, but not reflection, but the other one, when the angle changes because the density of forest and fields, the densities are different. It's sort of similar. I believe there's an analytical solution to it, but clearly there is a programming solution algorithm because like you obviously know that here the distance will be quite large and here's distance will be quite large as well because you have to like you may walk faster, but you walk a greater distance. So our intuition would be that something like in between is optimal, but closer to this point. And it essentially like traveling time will look something like that. Or actually traveling time will look something like that, I believe. So optimal point will be at least somewhat shifted to the right, point at which you enter the forest, but somewhat shifted to the right. And because you walk faster here, so you want to cover a larger distance here and smaller here. And this is clearly unimodal, so you can do ternary search. And you will need, like, you are given a point, you compute this distance, you compute this distance, you compute this time because you know speed, you compute this because you know velocity, right? You add them together, you compute total time. That's exactly what I do here. So here, like a unary function is actually much shorter. It takes 1 point, actually takes in coordinate at which we change. It computes the traveling time. And because traveling time is unimodal, you can then use ternary search to do all the work for you. Our ternary search is again a template, and it is not very different from binary search. Here you just need 2 middle values and you compare them between themselves. What I was saying like previously about this configuration of 4 values, in fact, you don't need it. You only need to compare these two. And like if middle that is righter, closer to the right than the other middle value is bigger, then you can discard left interval, left sort, and vice versa. So it's not the most efficient implementation because it does not discard like special cases when we can discard 2 sorts, but it doesn't like, in these cases we just get lucky, let's put it this way. This is more conservative implementation that always discards only 1 sort of your interval. On the bright side, it always runs in the same number of iterations. Because sometimes you don't know like to what precision you can compute the result, but you know how much time you have, and you can estimate the number of iterations based on how much time you have. Yeah, I guess this was it for binary search, ternary search, and binary search or the answer. Obviously, this is Codeforces gym. The link will be in the description. Also, so you can test your problems at Codeforces. Also, a link to my translations will be in the description and link to my solutions. I guess this was it for today. I hope this beginner-friendly topic was useful for you. I seen somebody asking for it in the comments, so that's why I decided to make it. If you have any other ideas that you want to some topics that you are more interested in than others, and let me know in the comments. We can totally do your personal request. I guess we'll do all trainings from 2012, 2013, and also 2013, 2014 season. There's around 30 of them. We already did 4. So I guess like a couple of trainings per week, I definitely can do it. So if you stay tuned for more videos, you will definitely get them, and you'll learn a lot. So I hope it was helpful, hope you enjoyed, and see you in the next one.